Welcome to this seminar on sustainability and cold-formed steel. This is one in a series of professional development programs offered through the Steel Framing Industry Association, or SFIA. The SFIA is a professional trade association consisting of cold-formed steel manufacturers, steel mills, contractors, designers, suppliers, and others in the construction industry. I encourage you to visit the SFIA website at cfsteel.org to check out the many useful resources available there. This course will introduce participants to the sustainability benefits of cold-formed steel in general. We'll focus on three major components of sustainability: material recycling or recycled content, energy savings the steel industry has achieved over time in producing the steel used for cold-formed framing products, and greenhouse gas reductions by the steel producers over time. After that, we'll spend the bulk of our time on requirements and opportunities to increase sustainability with cold-formed steel under the U.S. Green Building Council's LEED system. There are 4 learning objectives for this learning session. At the end of this course, participants will be able to identify recycling benefits associated with the use of cold-formed steel framing, identify progress made by steel producers in reducing energy use and greenhouse gas emissions, have a basic understanding of the latest version of LEED, and be knowledgeable of the specific LEED requirements that are associated with cold-formed steel and the resources available to assist in meeting those requirements. Note that achieving credits under LEED rarely happens just through the selection of a single product. Most often, the selection of a product and how it's used helps the designer to reach a threshold where the overall project earns points under certain credits. My main goal is that you'll leave here today with an understanding of what specific LEED requirements and credits cold-formed steel can contribute to in achieving on a project, and some understanding of how CFS contributes to those credits. There are 6 main topics. These topics include recycled content of CFS, energy use reductions with steel production, greenhouse gas reductions with steel production, introduction and background on LEED, specific LEED requirements that relate to CFS, and available tools and/or methods for meeting requirements. Let's start with recycled content. The use of recycled steel has its impact on both energy consumption and greenhouse gas emissions. Steel, since it's magnetic, is fairly easy to extract from a waste stream. Currently, on average, 80% of post-consumer steel is recycled. However, steel usage is segmented by industry, and the recovery rate for construction is 85%. This is a measure of how often a product is recycled at the end of its useful life. Steel's high recovery rate is a direct result of the fact that it is a cradle-to-cradle material, constantly being multi-cycled into the array of steel products in our economy. As reported by the Steel Recycling Institute, steel is the most recycled material. It exceeds the combined amounts of paper, plastic, glass, copper, lead, and aluminum. The industry goal for recycled steel in construction will be 90% by 2050. It already stands at around 87%. Recycling of steel not only saves on raw material extraction, it also reduces greenhouse gas emissions. For every ton of recycled steel that is used, we save 1,400 kilograms of iron ore, 400 kilograms of coal, and 55 kilograms of limestone. Here's an example of how recycling impacts greenhouse gas emissions. Bottom line, 340,000 tons of steel rail were recycled in 2007 alone, which amounts to over 800,000 tons of carbon dioxide emissions. That's comparable to the CO2 emissions from electricity use in over 121,000 homes per year. And that's all just from one steel product. Admittedly, the production of steel requires a lot of energy. However, the Steel Recycling Institute reports that between 1990 and 2010, improvements in the process have resulted in a reduction in energy use of about 27% for each ton of steel produced. Keeping in mind that anywhere from 20 to 40% of the cost of steel comes from energy, it stands to reason that there is a significant motivation to conserve energy. From a life cycle standpoint, about 8% of the energy consumed is in mining, preparation, and transportation of the raw material. In an integrated facility, that is one that has a BOF furnace and all the steps required to take the raw materials and turn it into a piece of steel, about 75% of the energy content of coal is used in the blast furnace. However, the heat it produces is reused in many ways throughout the manufacturing process, thus reducing or eliminating other sources or forms of energy. In the coking process, blast furnace and basic oxygen furnace output gases are being captured and reused. These output gases equal about 40% of the energy and are used as a fuel substitute. In other words, the process generates a lot of heat, but that heat is used elsewhere in the production process. Little is lost. Let's look further at energy use from a life cycle perspective. A life cycle assessment is an environmental impact analysis of a product that runs from raw material extraction, through manufacturer, product distribution, the product's serviceable life in place, till end-of-life disposal or recycle. The energy intensity of a basic oxygen furnace or BOF process is 31.2 gigajoules per ton. The energy intensity for an EAF process is only 12.5 gigajoules per ton. That's a 60% reduction. Along with the energy reduction is an emission reduction. Again, the main production worldwide for steel is still BOF, but there is a trend for increased EAF usage that is helping to drive energy savings. There are also some process changes or innovations that further help reduce the embodied energy. A few examples are scrap preheating, strip casting, and oxygen injection. A final thought here is that for cold-formed steel, the embodied energy is less than 13.2 million British thermal units per ton of steel. As a comparison, the Steel Recycling Institute states that the energy used in producing steel is approximately 19% of that used to produce aluminum. Here's an interesting way to look at energy use. This report was generated by the Athena Institute. It looks at embodied energy and greenhouse gas emissions from a system standpoint. As an industry, we tend to look at individual components that make up a system. That tends to exaggerate the impact of the individual components and doesn't provide a realistic look at what happens at a construction site. Here, we look at a simple metal stud partition and compare it to a wood stud and a concrete block wall. What jumps out first is the very small values we see for embodied energy. Second, we start to see the relative impact of greenhouse gases of steel-framed systems compared to the others. Looking specifically at North America, the steel industry has done an excellent job of reducing greenhouse gas emissions. The Environmental Protection Agency reports that the U.S. steel industry has reduced greenhouse gas emissions by 47%. There aren't many credible large building life cycle assessment studies conducted or funded by unbiased sources, but there are some on smaller buildings. In this example in Portugal, they compared life cycle assessments, or LCIAs, between a steel-framed house and a concrete house. The two homes were each a two-story single-family residence, as shown in the lower right. There were two main floors on each with 165 square meter floor area, and the top floor with 115 square meter area. The steel-framed house was sheathed with OSB on the outside and gypsum board on the inside. Rock wool insulation filled the stud cavity, and EIFS was the outside finish. The study considered a 50-year life cycle with 3 scenarios at the end of its service life. It was financed by the Portuguese Ministry of Science and Higher Education. The study was titled Life Cycle Comparison of a Lightweight Steel House versus a Concrete House. One of the highlight statements in the study is that the reuse of steel allows saving of approximately 50% of embodied energy, which would otherwise be wasted. Further conclusions in this study stressed the life cycle advantages of steel, and specifically steel's recycling and reuse attributes. Given the advances the steel industry has made toward developing more sustainable materials, we next want to see how this translates into application, particularly with regard to the LEED program. As you see on this slide, LEED stands for Leadership in Energy and Environmental Design. LEED was developed by the U.S. Green Building Council, a nonprofit formed in 1993. The first version of LEED was introduced in 2000. LEED version 4 is the primary version now operating. However, it's possible that you may see some mention of LEED 2009. Although it closed for registration in 2015, some of those buildings that got in under the 2009 version might not be finished to date. Any new projects must be registered to meet the version 4 requirements, with some clarification that I'll get to in the next slide. Although it does branch out into operation and maintenance, land development, and even citywide projects, LEED basically impacts the CFS industry as a rating system for new construction projects and existing building improvements. It is not a system that mandates specific materials over others. As the industry adapts to LEED requirements, the USGBC has continually modified the LEED program. This is both intentional to push for higher levels of sustainability over time, but also to address the need for improvements. It can be a complex process, and both LEED's content and process are evolving. Although we stated that LEED version 4 is the current version and the one we'll focus on, there is an asterisk from the prior slide that needs to be mentioned. A newer version, LEED version 4.1, has been released, but it is still a beta version. There is no date yet set where LEED version 4 will close for registration of projects, nor for version 4.1 to move out of beta status. Given the process in the past with introduction of new versions of LEED, it's likely that LEED version 4 will be around for the foreseeable future, and then there will be some overlap with version 4.1. It may be several years before version 4.1 is mandated and version 4 is completely phased out. Another reason USGBC continues to update LEED relates to their long-term goals. If you look at the different levels of LEED on the far left here, that is the platinum, gold, silver, and certified levels, you see that they fall below the zero impact horizontal line. In subsequent versions of LEED, represented by the different performance levels to the right, they move closer to the zero impact line, and eventually the gold and platinum levels move above that line. What this represents is that LEED is currently attempting to reduce negative environmental impacts of buildings, but will eventually move toward buildings that have positive impacts. I'll explain more about the different LEED levels shortly. So, how are they doing? It's not hard to argue that LEED is the most successful and widely recognized rating system for environmentally sustainable buildings, and its influence is growing globally. In 2019, USGBC announced that they've exceeded 100,000 commercial building projects using LEED. Their website states that 165 different countries have projects using LEED. With version 4, the number of registered projects now exceeds 1,000. How about in the United States? At the top are the numbers of U.S. projects that have achieved a certain level of performance as of the end of 2017. Note that the smallest numbers are those projects reaching the highest or platinum level. Most projects tend to end up in the middle, gold or silver levels, although there are a significant number who seek out the lowest or certified level too. The left bottom chart shows the projects that have registered, meaning that they're working towards certification at the end of the process. The increase over a relatively short time frame to over 65,000 projects is impressive. How many have followed through to actual certification? This is shown in the lower right chart. It's not clear why slightly more than half that are registered actually reached certification, although some of this may be due to a time lag. In other words, a large number of buildings have registered in the latter part of the chart on the left, and many of those may still be in the design and/or construction phase. So what's new with LEED version 4 versus the 2009 version of LEED? First, USGBC has indicated that there was a need to emphasize transparency with regard to what's in a building, while also ratcheting up some of the performance requirements. They also added some new credit categories dealing with items such as LEED processes, location and transportation considerations, and some international requirements. But the most relevant and significant changes related to CFS are a complete rewrite of the Materials and Resources section. The bottom line is that this version of LEED is very different, especially as it impacts CFS and other building framing materials. The Materials section now emphasizes transparency more than ever. As we've stated earlier, LEED is a rating system, but actually a better way to state it is that LEED is a series of rating systems, beginning with building design and construction, referred to as BD+C, and down through cities and communities at the bottom. You must get to at least the certified level to claim LEED status. Now back to the materials discussion. This is the most relevant category for CFS framing. You see here that the total possible number of points in this category is 13. But CFS, or any material itself, won't necessarily contribute to achieving points in every credit category, nor will all points within each credit always be available. Putting the 13 possible material points into perspective, the base certified level requires 40 total points, so 13 is nothing to look down at. At the other end of the scale, the platinum level requires 80 points, so every point is critical if that's your goal. I should also note that there are mandatory requirements for some credits you must meet as a prerequisite before achieving any of the other points in the same category. For example, the storage and collection of recyclables and the construction and demolition waste management planning are required before any of the other voluntary credits would be applicable. In most credit categories, you can earn 1 or 2 points depending on the level of performance you achieve. Building life cycle impact reduction is the exception, with up to 5 points available. We'll go through each of these items, starting with the 2 in the red box first, since they're 2 of the more important credits and ones we often get requests about, specifically regarding how they impact CFS and steel in general. Let's start with some background on life cycle assessment, or LCA as it's usually called. What is it, and then how is it used by LEED? LCA is not without its detractors. It has a subjective nature to it. It's more of a comparative tool between different processes, systems, or products. But in any case, LCA is now part of LEED and many other rating systems, so you need to understand it and how it impacts your products and industry. Version 4 is really the first version of LEED to emphasize LCA. LCA is a standardized process or method used to evaluate potential environmental and health impacts throughout the life cycle of the product, service, or process being examined. If you look at the steel life cycle shown here, it's pretty much a circular life cycle when recycled content is taken into account. With an LCA, you would look at the impact through all of those steps along the way. An LCA has 4 main steps. First is the goal and scope definition. At this step, you define the study, including items such as system boundaries. Once you know what you're going to study, you conduct an inventory analysis. Energy and material use, waste generation, and recycling, among other data, are collected for each step in the life cycle. Once the data is collected, you look at the impact of that information, things like emissions and waste loads, which impacts they cause, and what the magnitude of those impacts are. The last step, interpretation, is kind of an iterative process that happens throughout the study to check that the data is correct, of high enough quality, and that the system boundaries are appropriate. This slide shows the impact categories of a typical LCA. These are not all possible indicators, but are the ones currently used by most LCA practitioners. There are important other impacts that are often not reported, either because they have not yet been included in some of the software used for LCAs, the data for them has not been collected, or is too difficult or costly to collect. The study boundaries are not drawn broad enough, or their inclusion has been resisted effectively by special interest. For example, land use impacts and habitat disruption are important indicators for materials that rely on land clearing, such as wood framing. However, many industry studies have been careful to draw LCA boundaries so that these impacts are excluded from the system. Global warming potential is often viewed as the most important, and in some rating systems or green codes is given a higher value over other indicators. It looks at aggregated greenhouse gas emissions or the potential effect on warming the atmosphere of the planet. Next is ozone depletion, or basically the emissions that thin or cause holes in the ozone layer. Acidification potential is from emissions that cause acid rain, which we hear about frequently. Smog potential are emissions that form ground-level ozone or smog, and eutrophication potential is from nutrients that are released to the air or water and cause impacts on wildlife, water supplies, and similar effects. Life cycle impact is incorporated into LEED at both the whole building level and the product level. The first optional credit for earning points under the Materials section is called Building Life Cycle Impact Reduction. It comes with the ability to earn up to 5 points using 4 different options. The first 2 options, historic building reuse and renovation of abandoned or blighted buildings, offer the maximum 5 points, but unfortunately they aren't really important to CFS framing. Options 3 and 4 are more directly related to CFS. Option 3 allows a product to earn points by reusing buildings, sections of buildings, and materials such as steel. You can earn 2 to 4 points with projects that, for example, reuse steel partitions. This option is also limited as far as its applicability to most new construction, but it still shows some of the sustainability benefits of steel, such as durability and flexibility, that can enable reuse. To this point and throughout the presentation today, I'll go over the sections that relate to points available for use of steel framing, but we won't get into how to qualify since that often requires some significant effort and even some third-party design experience or input. I will give you some resources that contain more information later on in the presentation that you can begin to use to explore these topics in more detail. The whole building life cycle assessment option is the last one shown here for this credit, and it's definitely one where outside professional help would be needed. You can earn up to 3 points for a whole building LCA, but before the design team can move forward with a whole building LCA, they would need input or data on all of the materials and processes in the building. For example, you would need data on the processes and materials that are used up front on the building, data during operation throughout the lifespan of the buildings, and data on what happens at the end of the building's life cycle, such as recycling of materials. There are multiple software tools available to conduct an LCA, and at least 2 are specifically recognized in LEED. The steel industry, through World Steel internationally and AISI for North America specifically, have been involved in long-term efforts to collect and disseminate data related to steel products. At the product level, LEED version 4 has a credit for Environmental Product Declarations, or EPDs as they're often called. An EPD is basically a summary document that reports LCA information for individual products. As you see from the intent of this credit, LEED is focused on transparency by encouraging the use of products for which lifecycle information is made available. LEED also makes points available for products that can show improvement over others. This is shown in the LEED version 4 credit called Building Product Disclosure and Optimization. This credit allows a maximum of 2 points to be earned, or 1 point for each of the 2 available options. The first option is all about disclosure. The intent is to encourage use of products from manufacturers or industries that have collected and published an EPD on their products. It doesn't really matter what the impacts are, just that the information is disclosed. We'll talk more about EPDs later, but for now, the important distinction is that an EPD provided for a specific product from a specific manufacturer is differentiated from one developed by an industry for commodity or generic type products. For example, if Company X produces an EPD for their specific C-section stud, it would be counted as a whole product. Conversely, an EPD produced by a trade association for generic C-section studs would be considered half a product for the calculations under this credit. Thus, to receive the option 1 point using industry-wide EPDs would require 40 products to meet the 20 product threshold for this credit, versus 20 products if using all product-specific EPDs. This credit relates back to prior comments about a specific product by itself not achieving points, but contributing to the overall project achieving points. Unless you have 20 different steel products, all with product-specific EPDs, you would need to rely on other products in the building to achieve the points here. The third item under option 1 is another way to reach the 20 product threshold. But as you can see, it's worth even less than the industry-wide EPD at 1/4 product value. We won't get further into this item since it's mostly a moot point given that the steel industry has developed industry-wide EPDs for most products, including CFS, that are much more valuable for helping to achieve points under this option. Option 2 under this credit also offers 1 point, but it's a little different in that it gets into the relative performance of products in a building. The simplest way to state this is that the products in your building perform better in the impact indicators we discussed earlier. Remember, those are the emissions of greenhouse gases, ozone depletion, smog, acidification, and eutrophication. You need to beat the industry average in at least 3 of those categories. It would be nice if option 2 was as easy to use as option 1, but things never seem to work out that way in programs such as LEED. This credit is not based on the total number of products that meet a certain threshold, but relies on a calculation whereby the points are achieved only when meeting the improvement in 3 impact categories plus a cost calculation. The cost of the products that contribute to this credit must be at least 50% of the total cost of the building. Again, given that the cost of the structure alone will not likely reach the cost threshold, to achieve the point under this option will require multiple products that all contribute to the effort. Notice that the last item on this slide is a location valuation factor. This is an item that shows up in multiple credits throughout the LEED version 4 program requirements. We'll get into it in more detail here shortly, but basically it allows you to double the value for a specific credit when the product is sourced locally. This graphic is intended to show in summary form the process for developing an EPD and the relationship between the various steps. Keep in mind that this is a standardized process following standards maintained by the ISO, the International Standards Organization. The first step is to set the ground rules, and that is through development of product category rules. These govern the LCA study and EPD development. An important piece of the process is shown on the left as the LCI, or Life Cycle Inventory. This is basically the collection of data throughout the life cycle of a product. For steel products, this is information AISI and World Steel collect and maintain that feeds into the various software for an LCA study. The EPD is the summary of the impacts from this process. An industry-wide EPD for cold-formed steel studs and track is available. This was produced with broad industry participation under the direction of the Steel Recycling Institute, or SRI. The EPD is available through the link shown here and through the SFIA website. CFS is just one of the industry-wide EPDs available for steel products. As shown here, almost every steel product industry has worked with SRI to develop an EPD for their industry's generic products. This is important since many of these products are often used in the same building as CFS framing. Some individual CFS manufacturers have also developed product-specific EPDs. Let's get back to the location valuation factor we briefly discussed before. The intent of this credit is to reward manufacturers who extract, manufacture, and purchase products within 100 miles of the project by doubling their value. So rather than this being a standalone credit, it really is more like a multiplier for other credits. This is from the LEED version 4 reference guide to demonstrate application of the location valuation factor. The example here is for concrete material for a project based near Pittsburgh, Pennsylvania. The small circles represent the processes for the concrete products. Several of them are within the 100-mile dashed line circles surrounding the project location. But several, such as lime extraction and cement manufacturing, fall outside of that circle. Thus, the product would not qualify in this example. Although this credit is limited because of the rather tight criteria, it's worth examining because every point in LEED is important towards getting to the certified or higher level rating. We've spent a lot of time on LCA and EPDs intentionally because they're two of the more recent options for earning points in LEED with the help of CFS. SFIA and its members also are asked about these items on a fairly regular basis from architects, contractors, and others involved in design and bidding on projects. But you should be aware of some potential points in LEED version 4 that are also important to steel framing. For example, this slide is a good reminder that steel can help meet some of the LEED prerequisites, such as construction and waste management planning. Beyond the required planning, steel framing can also help earn up to 2 points for its actual contribution toward reducing scrap on site. So you may have been sitting here wondering when we'll hear about how the high recycled content of steel fits into LEED. That's always been a point of pride for the steel industry. The fact that steel has such a high recycled content and is infinitely recyclable. Although recycled content is still in LEED version 4, it's sort of been pushed to the background in favor of transparency issues, such as we see with EPDs now being encouraged. The sourcing and raw materials credit provides up to 2 points. Option 1 is another of these transparency items LEED is encouraging. This option awards a point for products where the manufacturer produces a corporate sustainability report or similar document that reports the environmental impacts with its product. Some steel mills produce these reports, but not everyone. An easier point under this credit is in Option 2, which addresses recycled content. As I mentioned, this used to be a more significant part of earlier LEED versions, but the direction LEED is taking seems to be more towards transparency or reporting and whole building performance versus the traditional sustainability issues, such as recycled content. But for now, this point is available. Steel is the only material recognized by LEED that allows a default value of recycled content, which is at 25%. You can often get higher recycled content values substantiated from a mill or supplier. The last credit shown here addresses material ingredients. This basically requires manufacturers to publish an inventory of all chemical ingredients in a product or to provide an alternative transparency report, such as a Health Product Declaration or HPD. Some manufacturers have developed inventories and/or HPDs, but they're far from mainstream at this point. However, it never hurts to inquire of your supplier or mill for this type of information. Our intent today was to provide an overview and highlight the LEED credits for which CFS has the most potential for helping to achieve points in LEED version 4. There are some resources that I want to mention that can help you begin to dive deeper into LEED and cold-formed steel. First, there's a fact sheet developed by the Steel Recycling Institute that covers the topics we went over here, plus a few others. It's available at the link shown here. This fact sheet addresses steel in general, so some of the credits may not be applicable to CFS products. SFIA also has a document on LEED available at www.cfsteel.org under the Resources tab of the website. This document is specific to cold-formed steel versus the wider steel products version from the Steel Recycling Institute, but both are good resources. The SFIA document also covers LEED 2009, the version that preceded LEED version 4. At this point, we are through with the formal presentation today. I hope you found value in the information and topics we discussed. You can also visit the SFIA website for additional information. Thank you for your time. And that the system boundaries are appropriate.